All right, hey chemistry class, Mr. Wood here again. The switch to ending on May 13th has caused me to kind of speed up my timeline a little bit. So consequently, we'll be skipping over some stuff, rearranging some stuff, and I hope you are able to keep up and figure out what's going on. I'll try to be more clear in what worksheet I'm on exactly and how we're at in the packet, and when we start the new packet, because we'll have to get through that too. So, right now I'm going to be looking at reaction types synthesis. This is a follow-up to reaction types decomposition because they're essentially the same thing. If you take a look, I have a list up here already. Synthesis types of reactions: direct, carbonates, chlorates, bases, and acids. That's exactly the same as our list of decomposition reactions because they're effectively the same thing. They're just going the opposite directions. Remember, with decomposition, you start with one compound and split it into two. With synthesis, you're starting with two compounds and squishing them together to make one, chemically speaking. So direct is the easiest one. That's like taking magnesium and oxygen and creating magnesium oxide, just like that. Or, hydrogen plus oxygen makes water, right? Nothing new there. Carbonates, again, if you remember, a carbonate is a polyatomic ion, CO3. So in a carbonate synthesis, we're starting with a metallic oxide, so some metal with oxygen, reacting with carbon dioxide, and that will make some carbonate. And again, I'll go through examples of all these in a little bit. Chlorates, again, start with a binary chloride, so some metal and chlorine plus oxygen will make a chlorate. Acids and bases, again, bases are a metallic oxide and water to produce a base. And then acids are a non-metal oxide plus water to make an acid. And again, these letters here are not actual elements, they're just placeholders. You can insert whatever you want there. So let's take a look at an example of each of these. I'm not going to redo direct because that's really pointless. You should be able to do that without any trouble at all. Let's look at carbonates. So carbonates, as you recall, start with some metallic oxide. Well, how do you know it's a metal? Well, because it's on the metal side of the periodic table. So if I take a metallic oxide like sodium oxide and react that with carbon dioxide, let me step back. If you just see that, you might say, that looks an awful lot like a double replacement reaction. You're right, but if you try doing it as a double replacement reaction, and again, note this is wrong, note what happens. So you're switching, right, the front numbers, the front ones, right? So we have sodium and oxygen and carbon, and it's the same thing. Nothing happens. Right, so that doesn't work out. That's a key to telling us that, this is probably a synthesis reaction, and we're going to form a carbonate. Now, again, the easiest way to do that is just to memorize these types of synthesis and decomposition reactions. So we're making a carbonate. What carbonate are we making? We're making sodium carbonate. How do I know? Because sodium is the only other thing in the equation that would work, right? Carbonate, of course, is a -2 charge. We have to balance our charges as always. And then I could go back and, actually, no, I don't need to balance the equation because it's balanced already. Never mind. So that's carbonates. That was type 2 carbonate reactions. Okay? Easy enough. Let's move on to chlorates. Chlorates take some chloride, say potassium chloride, react it with oxygen. And again, you might say to yourself, that looks like a single replacement reaction. Yeah, kinda. I see your point. But you have to know and recognize your synthesis reactions. That's why you don't do this. That's why we learn this kind of stuff, right? So you can tell the difference. This is going to make a metallic chloride. Excuse me, it's going to make chlorate. I said that wrong. So chlorate, ClO3, 3. And what chloride is going to make? Potassium chloride. It's the only one we have. Balanced charges, that's done. So, and it's balanced as, oh, it's not balanced. I could balance it quick here for us. Let's see here. That needs to go to a 3. That's a 2, and that's a 2. There, that's balanced. Okay. Chloride plus oxygen makes a chlorate. The last couple, bases are real simple. All right, bases, remember bases, anything that's a hydroxide. So I take a metal oxide, say, I don't know, calcium oxide, and react it with water, and we will make calcium hydroxide. Just like that. Again, the subscripts come from balancing the charges. And then the last type, acids, again, what we dealt with before, a non-metallic oxide, let's say in this case nitrogen. And remember, non-metallic oxides are a little tricky because they don't do charge very well. They actually do oxidation state, so it's a little different. So when that reacts with water, I know I'm going to make some combination of that. Acids start with hydrogen, it has to contain nitrogen, it has to contain oxygen. And the question is, which one will it make? We have to go back to our idea of oxidation state again. So really, I have two choices, right? What are my two polyatomic ions with nitrogen in them? Well, we have nitrate and nitrite. Those are my two choices. The question is, which one matches our condition over here? Well, if I uncross my charges, this would be a 2 and that would be a 5, and that matches. So this must have an oxidation state of a positive 5. So the question, which one of these two has an oxidation state of positive 5? Well, okay, oxygen has to be negative 2, so this total tide here is negative 6. So positive 1, oh, there we go. Just for grins and giggles, let's take a look at the other one. That'd be a negative 4. That's a 1, so that must be a 3, right? That wouldn't work out. So I would make nitric acid HNO3 instead of nitrous acid HNO2. The oxidation states don't match, so you have to make sure your oxidation states match. I'm going to do one more of the acids because they can be just a little bit tricky, and then I'll cut you loose to work on your problems. The other example they give, P2O5 plus water will form some acid. So again, I know it has to have hydrogen with it, I know it has to have phosphorus in it, and I know it has to be oxygen. So I'll take a look at my acids. What are my polyatomics containing phosphorus? Well, I have two choices, phosphate or phosphite. This is again why we learned all of those, right? So H3PO4 or H3PO3. And the question is, which of these two conditions match our condition on this side? In this case, phosphorus have to have an oxidation state of 5, right? Because we have to uncross our charges, so to speak. And we figure it out. Okay, oxygen is always negative 2. So this side would be negative 8. 3, that makes this 5. Boom. Again, just for argument's sake, let's check this one out. This would be a negative 6. So this is 3. So that must be 3 to balance it out. So to match our 5 oxidation states has to be our top one, H3PO4 or phosphoric acid. All right. Hope this helps. Hope you're understanding this reaction stuff. Again, if you need help, have questions, let me know. Your assignment for next time, of course, is to do the practice problems at the end of that section. Just 10 of them. Hopefully you won't have a problem with it. Let me know if you need some help. Have a good day.